All right. So 33 of you would like to see more really complicated non-examinable stuff. That's awesome. I will do that. But 41 of you would like to spend more time on Git and SSH, so I will also try and do that. That's going to be a real difference one. We're going to do a bit more on unit tests, and I will put some stuff on Maven and test coverage later on in the course. Okay, let's go on to the next question. This one is less facile. Okay, so for the 13 of you who aren't sure what instruction coverage is, please go back and watch the amazing video of last lecture, where hopefully I did explain what instruction coverage was. Chime will tell you off if you don't have enough instruction coverage in your test, so it's an important thing to understand. For the two of you who think that 100% instruction coverage means your program is bug-free, I'm really sorry, that's wrong. Here is a program. So here is my function sum, which is supposed to add x and y together, and it has a small but subtle bug. And then here is my test, which checks that sum of 1 plus 3 is equal to 4. This has 100% instruction coverage, but the test is still wrong. So the reason why I'm putting this in here is firstly to remind everybody what I mean by instruction coverage and what Chime means by instruction coverage. And secondly, I want to remind you all to take it with a pinch of salt. And test metrics are only really estimates about how good or how useful a test is. A test is really useful if it finds a bug, right? So this test fails that definition rather spectacularly. So don't just assume that 100% instruction coverage means that you've covered all of your options. There are other kinds of coverage. So there's path coverage, like have I explored all the different routes through my program? And then there's one whose name I can't remember, which is like domain coverage or something, which is sort of like have I tried every possible value that could go through my program? And so something like domain coverage, 100% domain coverage would have caught that, but it would be quite a long-running test. Okay, so just to remember, there's a take-home programming test to do in April. There are no ticks to do for object-oriented programming. You should complete the practical exercises at your own pace. If you are one of the 67 people who ticked last week that you've never done any Java before the pre-arrival course, and you're finding it difficult to keep up with the supervision work, I don't mind. You can do the practical work over Christmas vacation. You can do it next term. Chime will stay online for the whole of the year, so you don't have to sort of try and get it all done on a schedule now. But do try and go through the exercises. The take-home test is in April, and it's pass-fail worth 2 ticks. Someone asked me at the end of the last lecture whether the test was optional. Yes, it's optional in the sense that if you don't want those 2 ticks, then you don't have to do it. But if you would like those marks in your exam, then I recommend doing the test. Okay, so today we're going to talk about types, objects, and classes. And I just have four objectives. So firstly, you've seen a lot of procedural Java in the pre-arrival course, but we're just going to sort of do a quick recap and remind you of some of those bits. I'm sorry to the 45 of you who said you want arcane, non-examinable Java. I haven't put any in this week, but I will on Wednesday. The next thing we want to understand is something called function overloading, and this is the Java definition of function overloading. Then we're going to talk about the difference between a class and an object. And objects are this sort of key core part of object-oriented programming. It's not just a clever name, and I want you to know the difference between those two things. And then finally, we're going to look at something called constructors for how we build objects. So there are two sort of main types of programming language. So there's declarative languages, which specify what to do but not how to do it. So if you have built a web page in HTML, then you said, I want a heading, but you haven't said to the browser, please move your little drawing pen over to here and set it to be this size and then write some text. You've described what you want, not how to draw it. SQL, for when you start the databases course, when you say select star from table, you're saying give me all the rows from the table. You're not saying open the table, start at the beginning, iterate through one by one, adding them to a list. So that's a declarative approach. Java is an imperative language where you specify both what you want and how you want to do it. So you say take the value in x and update it with the value of x times 3. And, or you might say x plus x plus x, I suppose. But that might not be so good. So why are we learning Java? Well, if I go back in time to 2016, I can argue that Java was a useful language to learn. There's another language in this list which I want to highlight to you, which is this amazing programming language called Prolog, which I lecture next year. And so for those of you going on to 1B, look forward to Prolog. Prolog is another declarative language where you write down logical statements that you want to be true, and Prolog finds a way to make them true for you. So Prolog, look forward to that. And that's the top 40. If we move on, this is the rest of the top 50. Rust is only slightly more popular than Bash. I suspect that has changed since 2016. Bash is having a great renaissance. And here is the next 50. Yeah. Right. So functional languages are a subset of declarative languages, and OCaml, SML are functional programming languages. And it may appear that you're telling ML what to do, but really what you're doing is giving it like an example of what you want to happen. You're saying, if I get the factorial of 1, then the example of what you give back is 1. And the really interesting and really cool thing about functional languages, and sly digs aside from the previous slide, what's really cool about them is they give the compiler huge amounts of scope to optimize your code. So what actually gets run is not very, very much the same as this, but it does produce the same result. Optimizing compilers also work for imperative languages, but they have to work a whole lot harder because they have a whole lot less guarantees about what your program is actually going to do. So in ML, you had functions, and in imperative languages, we might still use the word functions, but we will reserve it for pieces of code that execute without a side effect. So if you look at this Java code here at the bottom of the slide, whenever I run this function m, it returns x times y. Well, that's a bit interesting. Imagine that's x times x. Returns x squared, but it has a side effect of updating this variable that's outside the scope of the function. So I would try to avoid calling m a function, and I might call it something different, like a procedure or a method, to try and make it clear in my head that this thing has a side effect when I run it. I can't just run it over and over again and expect the same thing to happen each time. Now, it's possible in ML to write functions with side effects too, and I think you do that in lecture 11. You do it with something called a ref. But for the most part, ML, because everything is immutable and everything is side effect free, we just talk about functions for the whole thing. So in Java, I might use the word function. Hopefully, I'll use it in the context of a function without a side effect. And otherwise, I might talk about methods or procedures, and those are things that alter state. Now, because you can alter state, that means that your method doesn't have to return anything at all. And so in Java, we have this idea about void, which also exists in C. And a void procedure doesn't return anything at all. Have you done unit yet in ML? Yes. So unit and void are not quite the same thing. And if you look forward to part 2 in the types course, then you will get a formal definition of why unit and void are not quite the same thing. For the moment, just sort of put them slightly differently in your head. A void procedure returns nothing in Java. You can't assign it to any value at all. From the pre-arrival course, you should remember count equals count plus 1, count plus equals 1, count plus plus, and plus plus count, and be able to tell me the difference between all of those. If you can't remember that kind of stuff, just go back and check it out again. The other thing that we did in the pre-arrival course was control flow, and rather than talk through all of these, we're just going to write some code. So I'm going to write a bunch of functions here for printing the numbers from 1 to 10. So can someone give me a control structure which I might use to do this? First idea? A while loop. Thank you. While loop. So I'm going to say x is 1, while x is less than 11, print x. Now remember, plus plus means post increment, so that prints the value of x and then adds 1 to it after that. And I can, run my code. So we're going to come back to this in later lectures, but this keyword static here is very important. And for the moment, just like we did with procedural Java, we need to remember to write it. And then in later lectures, I'm going to explain what it means. Oh, you just need to remember to write it in the correct place. OK, so that's a while loop. Give me another kind of control structure. For loop. OK, oops. Good tab complete there. Done. OK, another one. A load of if statements. I'm not sure how to do it with loads of if. I might do it with loads of prints. Here, look. And so on. if you'll excuse me typing that one. All right, give me another control structure. A recursive function. Oh, I'm going to stop at 11, aren't I? So I'm just hesitating slightly because I remember I said the numbers from 1 to 10, and I keep wanting to print the numbers from 0 to 9. And those kind of problems are classic computer science errors, which we all make. You notice I've got two versions of recursive here. I've got one that takes no arguments, and I've got one that takes an int. Those two functions are overloads of each other, and function overloading is something that I will come back to later in the slides. But for now, I want more control structures. Yeah. Do while. I've done loads of commercial programming. I don't think I've ever seen anyone use do while, but it's in there. Yeah, another one. Yeah. Oh, like some sort of like meta-programmed. Yeah, no, I'm not going to do that, but that's a nice, awful idea. Thank you very much. Something else? Yeah? Goto. Funny story. So Java, the word goto is a reserved word. Like you're not allowed to use it in your program apart from control, but it actually doesn't, like it's not allowed in the programming language. So they reserved goto just in case they might want it in future. And then thank goodness they decided they weren't going to have it. Good idea, though. Another one? Say that again, sorry? A while then a next method. Oh, a class with a next method. Yeah, I'm going to do classes, but not yet. But yes, hold that thought. Has anyone heard of streams? Right, let me show you something really awful. I mean, amazing. And you're like, Andy, you just promised us we were going to do a recap of procedural Java, and then you just typed stuff that doesn't make any sense. We're going to do streams like right towards the end of the course. This is a stream. This is like a generator for a stream. And this thing here is called a method reference. And I will come back to those later in the course. How about a for each loop? Anyone heard of a for each loop? Yep. So I can do list, integer, list, list of so if you If you notice, in IntelliJ, I'm not bothering to type system.out.println. Instead, you can type SOUT and then hit enter, and it types it for you. Someone showed me that last year, and it saved my demos like all sorts of key pain. You can also do PSVM, and that gives you public static void main. Again, like I've done loads of, in commercial programming, you don't write public static void main very much because like it's one program, it only has one main method and someone's already written it. But in demos, you write it all the time, so PSVM is surprisingly useful. Okay, those are all the ones I could have thought of. Blah, blah, blah. Right, so now we have some branching. So one way of doing branching is a return statement, and you saw that in the demo. We used return here in our recursive function to say, please stop running any further. I would like you to abort and leave the function. Another way of doing branching is to use break. So here is printing the numbers from 1 to 10 using break. Oops. So break in this context, break means sort of escape the looping or the control structure that's currently sort of wrapping around you. So we'll break out of the while loop. IntelliJ is really grumpy about this because it's saying you've got a conditional break inside an infinite loop. Why not write better code? And sometimes IntelliJ will try and fix things. Oh, it's used the do while loop. There we go. That's the second use of do while loop I've ever seen. Okay. I'm not sure I have a continue example. Here, look, I've got an example with the switch statement. How about that? Do while switch. This is a bit like your ifs one, whoever said the ifs one. While true. So we're going to say switch I. If I is 11, then we're going to break. Otherwise, if I is 1 or I is 2, actually you can just write default and that does all of them, print I. This break statement here is wrong because break statement in an if in a switch means please stop evaluating all these cases and exit the switch statement. So this program will run forever because every time it sees 11, it will just jump this block and go round to the beginning of the while loop again. Switch statements are this sort of really odd programming construct which Java inherited from C. There's a new kind of switch coming in Java 13, I think, or maybe 14, with sort of a more sort of like pattern matchy feel to it. But we don't get to play with that in this course. Does anyone know what I need to do if I want that break to actually break the while loop? Add a label. Yeah, so we don't have gotos, but we do have label. So I can say this. Yeah, so why am I showing you all these examples? I'm just trying to remind you of all of the different kind of control structures that you saw in the beginning in the pre-arrival course. I'm not expecting at the end of this course for you all to be language lawyers, right? I don't want you all to come out of this course going, I really need to know exactly what Java does in this particularly arcane, odd example. What I'd rather you did was came out of this course going, this is a nice safe place in which to write my code, and I'm going to avoid all of these icky edge places around the language. And then that way you avoid writing code which other people can't misunderstand. So that's a really valuable thing to do. And if you're using switch statements and breaks with values and things like that, then maybe it's worth thinking about whether you could just write something a little bit more natural like this. Okay, so in ML, up until lecture 11, all values in ML are immutable, right? Once you've put something into X, once you've said the value of X is 5, X has the value 5. In Java, once you say X is 5, you can then sort of change it later. You can say change X to be 7 or change X to be 10. So we have sort of like mutability built in. ML is a language of expressions. And what that means is that everything that you type in ML evaluates to a value. So if in ML I type x equals 5, then that's evaluated to the value 5. But if I type like an if statement, and it's got like an else and a then the whole if statement evaluates to a value as well. Right? So everything in ML is an expression, and that's a really sort of happy place to be, because everything is the same. In Java, things are either statements or expressions. So a statement does something, it has a side effect, but it doesn't produce a result. It doesn't have a value of its own. So in this example here, x equals 7 is an expression. Well, it's a statement expression, but for the moment, let's just say expression. And it evaluates to the value 7 with type int. It also has a side effect, which is to update the value of x to be 7. So it does two things at once, but it also evaluates to a value. Whereas if I say for I equals 0 to 10, print the thing out, then this doesn't evaluate to a value at all. This is just a statement. It doesn't have any like return value. So I'm just trying to make this point because there's a sort of a key misconception that people bring across from ML, which is that things have values, and in Java some things do and some things don't. And you need to just think about that because sometimes you want to return them and sometimes you can and sometimes you can't. So if we just have a little look at that. So if I write a function here, okay, it's the world's most complicated function. Returns 1 returns a value, the value 1 in this case, and I can store that in x. That will make sense. And if I print out x, then presumably you're all happy that this will print out 1. The next thing I can do is I can say int y equals x equals 2. So then what happens if I print x and y now? Hand up, someone? Both 0? Nope. 1, 0, and 1. Nope, they're both the same. X is 2 and y is 2. So this is an assignment, and an assignment takes a variable on the left-hand side and an expression on the right-hand side, which evaluates to a value. So in this case, it's nice and clear. The assignment has this expression here. This evaluates to 1, so x becomes 1. This is also an expression, the assignment of the value 2 to x. So this updates x to contain the value 2. That's its side effect. And it also evaluates to the value 2. So y equals x equals 2, sets x to 2, returns the value 2, and then sets y to be 2. The reason I'm showing you this demo is that I want you to be clear about the difference between returning a value and printing a value. So in ML, in the REPL, if you call a function and it returns, it prints something on the screen, right? It says, this thing returned 1. It's just returning a value. And in ML, you rarely print stuff out because printing is a horrible thing with side effects. Like it has an effect on the console, so we don't do that very much. In Java, we print lots, and we also return lots. So this function here is returning 1. That's a return. And then this thing here is actually printing it out onto the screen. So again, just think about the difference in your head, statements and expressions, and the difference between returning something and printing it out. So in ML, you got used to this idea of type inference, and it was really cool because you didn't have to type out all of the types of all these different things. It's also really cool because in exams, we can ask you what the types of things will be. Java and C++ have very limited forms of type inference. In Java 11 onwards, you can write var x equals 512, and Java will work out that you meant int for that. That kind of saves you a bit of typing. It's probably better to use it for places where like the readability of your program is not affected by people having to work out the type. Sometimes when you're given an ML function and you look at it and you're like, whoa, it would just really help to know what the type of this thing is. You can choose with Java how explicit you want to be and how much otherwise. So I would avoid writing programs where you only write var, for example. So Java distinguishes between primitive types and objects. So primitive types are things that the compiler just stores in memory and the machine understands for what they are. So int is a primitive type. In Java, it's a 32-bit signed integer. In C and C++, what it is depends on your platform. But normally it's sort of an integer-y thing. In Java, if you see a type written like a lowercase letter, that's a primitive type. Int, bool, short, char. These are all the float, double. These are all primitive types. Now, Java will automatically convert between different kinds of types for you behind your back in a very helpful way, in a way that's called widening and narrowing. And in general, it will widen stuff for free, but it will have to be told before it narrows anything. So, oh dear, no main method. Right. So I'm going to start off with a byte, and then I'm going to assign that byte to an integer. Right. So this is a implicit widening. Right. What I've done is I had a byte, which is only 8 bits, and I've stored it in an int, which is 32 bits, and Java has gone, no problem. 8 bits fits inside 32. I'll just do that for you behind your back. If I say byte c equals I, then IntelliJ says, can't do that. This is attempted implicit narrowing. And Java says, for your own good, I'm not going to compile this, because 32 bits might not fit into 8 bits. You might lose some data. Now, in our case, it does fit, because it's 10, but the compiler can't know that at compile time. There's a thing called the halting problem, which you learn about next year, in which you can unequivocally prove that the compiler can't know that about that at runtime. That makes you really popular at parties, so pay attention for that. OK, so I can't do an implicit narrowing, but I can do an explicit narrowing. So I can say, so what I've said here is, I know best. Promise you that if you just take this integer and throw away some bits, then everything will be good, so please let me treat that as a byte. So this is an explicit narrowing. And now I want to show you something fun. So if you call this call method on int to binary string, then you can get it to print out for you the binary contents of a file. And here you can see here it's printed out 8 ones, so 255 is 8 ones. So it's 8 bits. Right, so this is good. So I can say byte z equals byte j. I'm safe because it's 8 bits, right? And I can print it out. Anyone know what this prints? Prints -1. See, I told you that Java Puzzlers was fun, right? Right, so why has it done this? Well, it's done something called like sign extension and conversion and horribleness. Basically, 8 bits of an int, right, go on to 8 bits of a byte, but bytes are signed in Java, so the top bit of a byte in Java is a negative value. If you're doing digital electronics, you've done 2's complement, yes. If you're doing natural sciences paper 1, ooh. Now, system.out.println then goes, I know how to print numbers. I convert them to ints, and I print them out. So then it takes all those bits 1, and then it converts it back out to an int. So it copies, it sign extends that sign bit all the way out again, and you get back the number -1, and it prints it out. What's the point of this demo? Just be careful. When you start doing things like casting bytes to ints, it may seem like you're in sort of like doing things which are sensible. You might be. Just be really cautious about that. That's one of these points when you're starting to move away from sort of like straight, easy to understand code to things that you want to think about. If anyone ever asks you, they say, read 4 bytes from this input stream and convert it to an integer, the bytes are in big endian order, then all of a sudden you should go, hang on, I need to be really careful here, because I'm going to be converting things between each other of different sizes, and something's probably going to go wrong, and this is the example. What you would do if you're not sure, of course, is you would write lots of tests, which I'm going to come back to in a minute. OK, that was widening and narrowing. So I showed you the recursion example at the beginning of in the first demo, where we had 2 functions which had a different method signature, but the same name. They were overloads of each other. And it's kind of useful to be able to do that, because you can have the functions having the same name, so to the programmer, the person using your code, they can understand that they're all kind of the same thing, but you can take different arguments. And the way overloading works in Java is that you have the same function name, you have different arguments, and if you want to, you can change the return type. But if you only change the return type, then that's not an overload. That's just the duplicated function definition. Right? So Java distinguishes between overloaded functions on changes in parameters, not changes in return type. Later on in the course, we're going to do something called overriding. And overriding and overloading are very different things, but they look almost the same when you write them down. So just make sure you recall the rules for overloading and overriding. So the function itself, right, when we write int myFun equals int a, int b, it's made up of two parts. This is the prototype bit that tells us what the signature of the function will be, and then there's the body. I will probably use the word signature instead of prototype, but you can think about those two words being the same for the contents of this course. So the method signature determines which one we're going to call and what arguments it needs to have. We don't need to look in the body to know what it's going to do. So in OCaml, you might write something like the thing above. Does anyone know what that is? It's a lazy list. Yep, it's got this unit to thing going on there. Unit, remember, is slightly different to void. In Java, when you want to have a data type, you use a class. So here is our first class, vector3d, and it contains 3 floats, x, y, and z, whereas our lazy list contains 2 things. It contains a nil and a cons. Now, when we want to manipulate our lazy list, we write functions to do it. So here's the head function. When we want to manipulate our vector, we write methods inside the class. So typically, your class definition here consists of some state, so the values that you want your objects to have, and then some behavior, which are a load of methods which are going to act on those objects. And one of the things that is appealing about object-oriented programming is this idea of encapsulation, which I will come back to many times in the course, where we package together data and behavior into the same place so that then we can sort of work on them in the same way. So remember that your objects are broken up between state and behavior. You can write your object and you can actually spread your state all the way down through the object. So you can, like, if you want to, alternate methods and fields all the way down the file. But normally what people do is they put all the state and the source code at the beginning of the object, at the beginning of the class, sorry, so that everyone can see what's going on. So when I talk about state, I might be referring to things like fields, instance variables, properties variables, members. If you hear me say these words, then you can think to yourself, state. And if I talk about functions or methods or procedures, I'm talking about behavior. The purpose of this slide is just to sort of just give you a bit of a glossary about what these different terms might mean. Generally, just think about your objects being made up of state and behavior. So I've said class and object, and I've probably said class and object a few times now. Classes are templates for objects. So a class is sort of like a specification of what my object will be like when I make one. So the class is like the description of the functionality, and then the object is an instance of the class. So you have one class. In this slide, it's called myCoolClass. And then you can create as many objects as you like, which are instances of that class. And here I've got 2, m and n, but you could have as many as you want. So you have one class and then many instances of that class. You've seen classes already in Java. You've seen string, for example. So there's one string class, and then you can imagine there are lots of different instances of string that you might create. An instance of a class is called an object. You should be, at the end of this course, you should be ready. If anyone stops you on the street and says, what's the difference between a class and an object? You should be able to answer that question. So I've already shown you a class definition. You write public class vector3d. Public is an access modifier, which I will talk about later. Class is the keyword that says I'm defining a class. Vector3d is the name of the class. And its objects of that class, when they're created, will have the type vector3d. Vector3d contains some state, those 3 values, and it contains some behavior, that add method. Now, when I created my object, I call new to create a new one. If you've used Python, presumably many of you have these days, you don't write new. If you use C++, sometimes you write new and sometimes you don't. In Java, you always write new. So my object m equals new my object. What this says is it says to the compiler, I would like you to make a new instance of the class my object and store it in M. Technically, what you store in M is a reference to that object, and I will come back to that in lecture 4. So the right-hand side looks a bit like a function call, right? It's sort of like my object in brackets, and that's kind of exactly what it is. It's a call to a constructor. So the constructors of your class are the code that the compiler runs when it makes new instances of that class. And so you can use constructors to initialize the state of the class in a convenient way. So if you've decided, for example, that whenever someone creates a new instance of your vector, it should always be the unit vector, then you can initialize your state variables in that place. Or you could say that every time someone creates an instance of my object, the system should play the Windows boot up sound. And you could also write that code. So we use constructors to initialize the state of the class. When you write a constructor, you just write one with the same name as the class, and it has no return type. It's just like a syntactic way of telling the compiler that this is a constructor. So let me show you one here. So here's my class vector3d, and I've written a constructor, which is this thing in bold, which takes 3 arguments, xi, yi, and zi, and assigns them to the fields in the class. So this is a constructor. And if I wanted to create a new vector3d, I would call this code down here, new vector3d, of that stuff. If you have used the same names in your method parameters as the names of your fields, then you can use this special this word, which I will explain more detail about later, to disambiguate the names. So this.x is the x, which is the one that lives with the object. It's the x for this object. And if I write another constructor with a different set of parameters, then this is an example of overloading, because it has a different set of parameters. And I can have as many different overloaded constructors as I like, and I can therefore define some default behavior with them. OK, so this vector3d only has state. I haven't written any behavior at all. And Java then does something magic for you behind the back. And it says, well, you haven't written a constructor, so I'm going to provide one for you. And this is called a default constructor. So if you don't provide any constructor, Java will give you one that takes no arguments. So I can write vector3dv equals new vector3d with no arguments, and that will compile and work. And Java's just sort of made that up for me in the background. And if I don't initialize a field, it gets set to whatever 0 means for that type. So if it's an int or a byte, then it's 0. If it's a float or a double, it's 0.0. And if it's a reference, like something pointing to another object, it initializes it to null. But it's just always is set to 0. If you've done any C or C++, that's a different guarantee. What C and C++ says is that if you don't initialize a variable, it will just have whatever happens to be in memory at that point in time. Anything it could be. Sometimes it's 0, and you get lucky. As a general style point, remember what I said about language lawyering? Just avoid having uninitialized fields in your class, and then people who are reading your class don't need to know what the 0 value for that type is particular thing is. Right? Just set it yourself. OK, so before I conclude this lecture, I have a question for you. So I'm going to implement this method called isEven. So I'm going to say return x%2 is 1. OK, what does percent mean? Modulo, right? So it says if x mod 2 is 1, then x is even. And now what I'm going to do is I'm going to write a test for this one. So I promised to talk a little bit more about writing unit tests. So let me go into some detail here. So first of all, JUnit is only one of many unit testing frameworks. There are lots of other options. We're just going to use JUnit in this course. That's the one I use the most. So if you ask me questions about other ones, I probably don't even know the answer. Now, there are various versions of JUnit. We're using JUnit 4. And if you want to, you can add this thing at the top of your class file that says, I want this to be run with JUnit 4. This is called an annotation. And the compiler uses annotations as a way of getting some more information about your program that's non-executable. And I'll show you some more annotations in a moment. In the further Java course next year, we write our own annotations. You don't have to write that. If you don't write run with JUnit4.class, that's the default if you happen to be using JUnit 4. But if you want to be explicit, you can write that. Then for the purposes of IntelliJ and Maven, this word test in the class name is really important. So you need to call your class something test or test something to make sure that the testing framework knows to go look at them. Now, the next thing the testing framework does when I say run these tests is it takes this class, right, and it creates an instance of that object. It does that behind my back, calling the default constructor. Once it's created the instance of the object, it then looks inside the object and it says, what methods does this object have? So this is a feature called reflection, whereby a programming language can look at itself at runtime and see what programming aspects it has. So we can look at this thing at runtime, that's what JUnit does, and it says which methods does it have, and which of these methods are annotated with this annotation at test. So unless you write at test above your method, it won't get run. And believe it or not, well, believe it, it's super common for people to forget to write that annotation. They write their code, they push their code, they go into test, and they're like, hey, all my tests are passing. And it turns out, no, all your tests are not even being run. So don't forget to write test. That tells JUnit to run it. Then test methods need to be public and void. You just have to write that. That's magic. And then this here is the name. Now, those of you who are, have done a load of Java, you remember that we use this sort of naming convention where we have sort of like upper and lowercase letters, and we don't tend not to use underscores between things. That's like C and Python programmers do that. Apart from in test names. So in unit tests, when you write a test name, you try to be as descriptive as possible about what that test does and how it does it. And the reason why you do that is that most testing frameworks, when they run your tests, give you back a report at the end, and they give you a list of all the names of the tests that have been run and whether they passed or failed. And if you've named your test descriptively, then just by looking at the name, it tells you what went wrong with your program. And if you've named all of your tests, test 1, test 2, test 3, test 4, test 5, test 6, then it doesn't tell you anything at all, and you have to go and read your source code. So I would encourage you to try and name your tests as descriptively as possible. So here we have even returns true when it's even. So slightly tautologous, but there we go. So normally you would do some sort of structure like the thing that I'm testing, the value that I'm expecting to give, and then the circumstances in which I'm expecting that to happen. And if you follow that kind of pattern, then when you've got 10,000 unit tests in your code base and everyone's followed that pattern, it's much easier to debug when something goes wrong. Now, the next thing you'll notice about these tests is I've written something that's like extraordinarily verbose for what is just going, pass 4 and see whether it's true. And again, this is just for readability for other people who are reading your tests. You want your tests to read like a story to somebody. They don't have to think about it. They just want to see the structure so they know what's wrong with the program. And normally the structure of a unit test falls into these 3 blocks: arrange, act, and assert. So in the arrange block, you arrange all of your input variables to have the numbers in them or the contents that you want. Then you act, so you actually call your program and you collect the result from doing it. And then you assert at the end to check that the thing that you've got actually is the value that you want. Now, if you write all of your unit tests with this slightly verbose, awkward structure, then when someone comes along to try and debug your code, maybe it's you in the future, maybe it's somebody else, they know exactly what's going on and they can parse your unit test just by looking at it very quickly. So again, unit test good practice guides will talk about trying to use this structure of arrange, act, assert. You can even, if you want to, write comments, arrange, act, assert. You'll see that I've done that in all of the Chime tests. This is much easier to read than, for example, if I just like okay, so I could just write a very simple one-liner like that, but if I did that, you could say, okay, I can read that fine, but it doesn't have the same structure as all the other tests, and so your simple ones will read like that, and your more complicated ones will read like something different, and so on. So again, I would just encourage you to write something which has this sort of like very verbose structure. Okay, so I'm going to run my tests. Let's run them here. Whoops. Yay, unit tests. All right, so now my test pass. Hooray. Okay. Now I want to give you a Java puzzler, because it's such a fun book. What's wrong with this code? Pardon? X can be negative, right. So, let me just fix this up. IntelliJ has this thing for renaming a method, which I really wish I'd done now. But there you go. Let's just check that this works. So you said what happens when x is negative. So let's give it another one of these and pass it a negative number instead. So if I just make this -4, we should do the same thing. And if I make this -5, that should do the same thing. So then I can run my tests. And my test fails here. You see that in my test report. Because my tests are so brilliantly named, I could just stop there, but whatever. Oh, that's a nice typo. So let's say I want to find out what's gone wrong. Rather than adding hundreds of println statements, I'm going to use the debugger. So click next to the line you want to stop on. That inserts a breakpoint, and then you can then debug that method. And then remember, I've got these little arrows here. So this one means step over. So that means jump over the line and carry on to the next one. I don't want to do that because even is about to be run. So I want to see what happens inside it. So I'm going to use this down arrow, which means step in. So I go to step in, and it says, this is interesting. X is -5. And then it's just going to return. And I'm like, well, I'm not really going to learn very much from that. So what I'm going to do is use this cool evaluate expression window and see what happens. So I can say, well, what was x mod 2? And the answer is -1. So the bug in this program is that if x is a negative number, then the mod is a negative number as well. So how should I fix it? I could use absolute value. Yep. Yeah, not equals to 0.
Or even not is odd x.
Yeah, or even not is odd. Probably what I would also do now is I would write maybe or something, because someone might come along in the future and go, that's really odd. Why have they written not equal to 0? It might be much clearer to write equals 1, and then they introduce a bug. So sometimes feel free to add little comments like that in your program as a note to your future self to remind you why you've done something. Okay, that was a Java puzzler. And again, I'm not expecting you to know in the exam that mod of a negative number is a negative number. That I would count as language lawyering. But the reason I want to show you this example is that people will often tell you that software has bugs, and like all software has bugs. And I want to give you an example about how these things sneak into programs, right? You could write this code. It's your is-odd function. It's run really well for years. Someone uses it in a slightly different way, and then all of a sudden your code doesn't work anymore. This is why programs go wrong. Okay, next time we're going to talk about designing classes. I will post a video from this lecture online and link it from the course website. See you on Wednesday.